Now the next theorem we are going to see. If sorry, before going to the theorem, another one result is there. The set of all rational numbers is a first category. The set of all rational numbers is of first category. Why? Why it is of first category? Because you see, set of all rational numbers is countable. We know that the set of all rational numbers is countable. That is Q can be written as something like this: Q1, Q2, Q3. So already we proved these things. Set of all rational numbers is countable. And one point sets or singleton sets, say like this: Q1. Suppose I take the element and write like a one point sets. One point sets are closed. One point sets are closed in R. One point sets are closed. And nowhere dense. One point sets are nowhere dense because it contains only one point. How it can contain an open interval? So it's not possible. So always one point sets means it is always closed and it's automatically what? Nowhere dense. So here this Q can be written as union of all one point sets like this, where I equals to 1 to 2. That is, it is written as Q1 union Q2 union Q3 like this. This is the countable union. We say it's a countable union of, and each of them are nowhere dense sets. So this is the definition of this is the definition of a set is of first category. Please recall, when you say set D is of first category, it can be written like this: a countable union of some sets where each En must be what? Nowhere dense. Nowhere dense in R1. So here you can see set of all rational number Q is of first category because this Q can be written as union of one point sets like this. Each of the one point sets are closed as well as nowhere dense. So Q is of first category. So this one they can ask, prove that the set of all rational number is of first category. So this is the hints we have discussed. Now next we are going to prove a small theorem. If there are two sets A and B, both are of first category, then if they union them, then the resulting set is also of first category. That is a theorem. If A and B are sets of the first category, sets of the first category, then A union B is also of the first category. Very simple thing. If suppose If suppose A equals to union of Hn, where n equals to 1 to infinity, and B equals to union of something like En, where as per the we assume that A and B are first category, so where this each Hn and En, each Hn and En are nowhere dense sets in R1. That's by definition, because it is assumed that both A and B are first category. So I am assuming like this. So it should be Hn and En must be nowhere dense, each for each n. Then A union B clearly is the union of all Hns and Ens. So it will be combination of all Hn and En. And already we studied, if A and B are countable sets, the union of two countable set is also countable. Therefore, the union contains all Hns and Ens. So if the union of all Hn and En, then the resulting collection is also countable. So then A union B is the union of all Hn and En. Which are countable. Hence, A union B is a union of countable collection of nowhere dense sets. Countable collection of nowhere dense sets in R1. Hence, A union B is of first category. Hence the proof. So this completes the proof. And another one, note that we are going to prove this one. The whole real line is not of the first category set. It is not of first category set. We are going to prove this one, and this result we call it as Bayes' category theorem for R1. That we are going to prove now. Now, that is the next thing. So we are going to prove that is by a theorem. The set, that real line, set R1 is not of first category, means it is of second category. Is of the second category. So this is what we are going to prove now. Prove that set of all real numbers is of second category. Proof. Now we are going to prove this by, and the name of this theorem is, Bayes' first category theorem. Bayes' category theorem for R1. This is the name of this theorem. Named theorem. This is a named theorem. Sometimes they may ask you the question, state and prove Bayes' category theorem. Simple. The set R, the real numbers is of second category. That's all. Now we are going to prove this by contrapositive technique. We are going to assume that Suppose R1 is a first category, that's all. Let us assume that R is equals to union of Fn, union of Fn, where each Fn is nowhere dense in R1. That is, we are assuming that real numbers is a first category set. So I am using the definition of first category. Suppose it is union of Fn's where each Fn is a nowhere dense set. We assume that each Fn is closed set. Fn is a closed set. If it is not closed set, we will consider instead of Fn, we will consider Fn bar. If suppose Fn is not closed, then we consider that Fn bar instead of Fn. Now what happens now is, you see, what happens if Fn is not closed, so then F bar, we are going to use F bar instead of F. Further we know that since we know this that Fn is always, any set is a subset of its closure, that is not known to us, so which implies R which is equals to union of Fn, and this should be a subset of what? Union of Fn bar, because each of these Fn is a subset of its closure. And even Fn bar is any set real numbers, set of all real numbers, anything, set of all subsets of real numbers, everything subset of R. So the union of all these sets which are inside R should be again a subset of. So this implies that R can be written as union of, because you see here the left hand side and right hand side are same, but this is a subset of this. So only possibility is that everything must be equal. So we get like this. So just now we explained, suppose R equals to union of Fn where each Fn is nowhere dense. We assume that each Fn is closed. Okay, we assume it. If Fn is not closed, we will use here in place of Fn bar. For why we are using that, how can we use that, further the explanation is given here. Okay, so now we assume that each Fn is a closed set. Even if it is not closed set, we will use Fn bar instead of F. For that we are given the explanation. So R can be written as like this. So now here each Fn bar are closed and nova dense in R. Now we are going to do some construction. Now let us take any x1 that is not element of f1. That is not element of f1. Before going that, I will just draw this one. So now we are taking x1 which is not element of f1. Since each f1 is, we assume that each of the sets f1 f2 are closed. Since f1 is closed and nowhere dense, that is the assumption. Because why it's nowhere dense? Because we assume that it's a first category. R is a first category. So each f1 is closed and nowhere dense in R. Each f1 is closed and nowhere dense in R. So here each f1 bar are closed and nowhere dense in R. Okay. Now first we are going to consider x1 which does not belongs to f1. Like this one element we are going to consider. Since f1 is closed, that is our assumption. F1 is closed. There is an open interval. There exists an open interval I1, say I1, about x1 which does not intersect f1. The reason I am going to give, why? Because the reason is one theorem is there. That theorem we studied in closed sets. We cannot. So here you see, and right. Since the subset E of M, E is a subset of M, then suppose E is a subset of M, the theorem, what it says is, then X is element of M, the metric space, is a limit point of E if and only if whatever open ball we construct about the center about X contains at least one point of E. Using this theorem only we are telling this. How is it possible? How we are telling that there exists one O? See, this and all you can just rough side. So this is, suppose this is the thing, and we say that F1 is closed. F1 is closed. That is, it contains its own limit points. Suppose I say a point x1 is outside, it's not belonging to f1. Like this one point we have assumed. So if it is outside of x1, definitely this is not a limit point. If this is not a limit point, if it is a limit point, then whatever open ball we draw, it will contain some point of f1. Since this is not a limit point, definitely there will be one open ball. Definitely there will be an open ball or open interval which does not intersect f1. That is it. This theorem only we have used it. The contrary of this theorem. If it is not a limit point, then there exists at least one open ball which does not contain any point of E. So that is what. Since f1 is closed, there exists an open interval like this. Open interval is open interval I1. I name this interval as I1 about x1, that is center is x1, which does not intersect f1. This is possible because of this theorem. That is why we used this theorem. We can put a star here, and in bracket you can go by this result. You can write it. This and all you can write it in. Don't want to write in the main page. You can. This is also not required. Okay, but you have to write that statement. But because by star. Because this full statement we have used this theorem to get that result. Now what we do is, now let J1 be a closed interval, where the property that the length of the interval Jn, length of the interval J1 should lie between 0 and 1, such that another property is this J1 must be a subset of I1, must be a subset of, like this one interval, closed interval, we are forming one closed interval. This is a construction. Let J1 be a closed interval which is inside this I1. If it is inside I1, I1 itself does not intersect F1. So J1 also will not intersect F1. And what is the length of J1? It should follow this property. Then if we choose like this on interval J1, then definitely this J1 intersection F1 is what? Empty. There exists no intersection. There exists no intersection. There exists no intersection. I will be shading this, these things. This is the theorem, we used it. And these things is not required in the main part. This is just for our explanation. Okay. No need to draw anything. Okay, if J1 is chosen with a closed interval, I will draw the figures again very clearly. Again I will open the box. Suppose a real line, take something like F1 is there. Suppose this set is F1. First we create another set interval I1. I1 is what? An open interval. Something like this. Suppose I1, this interval is I1, which contains x1, whose center is x1. Okay. Center means it should be like this, no? Center. Okay. Suppose this is I1, an open interval whose center is I1. That is what you see. I1 about x1, which does not intersect F1. Clear. But F1 is a closed set. Okay. And next what we create is set J1. So closed interval which length is less than 1, but J1 is a subset of I1 J1 is a closed interval, something like this. You think, imagination, this is what J1. So suppose this interval is J1. Okay, so now clearly J1 intersection F1 is what? Non-empty, clear. So for that purpose I have done this. Still we will come back to this construction later now, one by one. So now this first step is over. Now consider another set F2, the second one of that union F2, which is also what? Nowhere dense as per the definition, dense, and thus nowhere dense means it does not contain an open interval. Thus does not contain all of the interior of J1. J1 is a closed set, so it has an interior. This is the interior except the two endpoints. This is the interior. Interior means all points inside of the interval. Interior is an open set. But what is the definition of F2? F2 is a nowhere dense, so it cannot contain any open interval. So we are going to link this F2 and this J1 now. That is what we are going to do. So now this F2, we are going to compare this F2 and J1. So the interior of J1 is an open set. Suppose this is J1. This is called the interior of J1. This is called the boundary. This interior is the open set. Okay, so since F2 is nowhere dense, it cannot contain any open set, and hence this cannot contain the interior of J1. That's all. That is what we are going to use. So it does not contain all of the interior of J1. This is because F2 is a nowhere dense. Here what is an interior of a closed set? It's nothing but the corresponding open interval. The interior of the closed interval AB is the open interval AB. That is, for example, this is the okay, I will draw it more clearly. Suppose this is the A, B, this totally all points in between them, everything including A and B, we call it as A, B, closed set. Only these points excluding A and B, we call it as open interval. More particularly for this set AB, this is called as an interior. Interior of the set A, comma. So these things is not required for the proof. Simply you can understand. Okay, just for our understanding. So now that is so it does not contain all the interior of J1 because J1 is a closed set and the interior is open. Therefore, F2 cannot contain all the interior of J1. So now that interior of J1 will not be completely inside what? F2. So we are going to take one more element called X2. That is what is this. I will come back to this construction here. From here, first I will write it. Now, let us take a point, any point, say I name it as x2 in the interior, x2 in the interior of J1, where J1 is closed just now, such that this x2 is not belonging to f2, because not every part of this interior will be inside f2. Some part will not be inside f2. So that part I am going to consider, and that element I am going to take from that part is x2. So definitely x2 does not belong to f2. For that only explanation is given. How x2 cannot belong to f2. For that only we have given this explanation, and this is a nowhere dense and f2. And we think that this is something x2 that is taken from J1 only. Now we are going to create the next set J2. That is the next step. Then see, this x2 is not belonging to f2, where f2 is closed. We are going to link that one. x2 this not belongs to f2, and f2 is closed. This implies that there exists an open interval. Say I2, same like I1, I2 about this point x2, which does not intersect what? f2, such that this I2 must be very important. This I2 must be inside J1. This is I2. So I have taken x2. This interval is J1. Now I am going to take another interval that is called as open interval, that is called as I2, something like this. Okay. This interval, we name it as I2. I2 must be a subset of J1, and next after this I2 we are going to construct another one closed interval like this. This is J2. This is how the sequence goes. Like this, we do keep on constructing I1, I2, J1, J2, goes on like this. Okay? F2, I2 is all I1, I2, I3, all see, all this I1, I2 are all what? Open set, open interval, and J1, J2 are all what? Closed. This one you have to keep in mind, so don't get confused. Now we are going to create, already we created one set J1, that is an closed interval, but the length of J1 is less than 1. Now we are going to create another interval J2. Let J2 be a closed interval, with length length of J2 is less than 1 by 2 such that this J2 is contained inside I2. That is very important. Then clearly this J2 intersection F2 is empty, because F2 definitely does not intersect what? I2. So here this is open interval I2 which does not intersect F2. This I2 itself does not intersect F2, and J2 is inside I2, therefore J2 also will not intersect F2. That's why we get this. So our aim is to create sets like this. By continuing this process, like this, we may construct a sequence of non-empty closed intervals, say J1, J2, and one more thing, see this J1 contains J2, J2 will contain J3, okay, like this only it goes. And very important thing is J1 does not intersect F1, J2 does not intersect F2, J3 does not intersect F3, it goes on like this, such that. And how are the lengths of this J1, J2, J3? Such that in general the length of any Jn is less than 1 by n. Please see, put 1, J1, the length is less than 1. In J2, this length is 1 by 2, less than 1 by 2. The length is keep on decreasing, that's what. And another thing is, each Jn, if intersect with the corresponding Fn, that is what? Empty. Like this only we have constructed. So finally, we list all the properties of the sets between Jn and Fn. We enumerate this one. Okay, we list all the things whatever we have done in the construction in a single line, in a single statement. Okay, like this. So now we are going to use nested interval theorem by nested interval theorem, there is only one point. There is a point, say y in R1, which is contained in this intersection of all J's. This is by nested interval theorem. So what is that nested interval theorem says? What is a nested interval theorem says, which is studied in sequences of real numbers? What is the theorem says is, for each n in I, let In be the closed intervals such that I1 contains I2, I2 contains I3, it goes on. Sequence In into In plus 1, and the lengths of each of these intervals keeps on decreasing. Keeps on decreasing. The lengths of each intervals keeps on decreasing. Then if these two happens, then the intersection of all these intervals contains precisely one point only. So this is the nested interval theorem. You see, our interval J is closed. It all satisfies the hypothesis of this nested interval theorem. You can see the intervals J1, J2 keeps on decreasing. See, it satisfies this one. In place of I1 you put J1, and when n is large, what happens is the interval's length is keep on decreasing. You see, if you put n tends to infinity, the length of Jn tends to 0 nearly. It satisfies both of them. Therefore, the intersection of Jn contains only one point. How we got this result? That is by nested interval theorem. Essentially, only one point is there in the intersection of all Jn. Hence, now for each n, y is in Jn, and hence y is not in Fn for any n. See, if it is this y is belonging to all this intersection, so in this intersection which has only one point, that is y. That is, y is element of J1, y is element of J2, y is element of J2. If y is element of J1, then y cannot be in F1. That is how we constructed. Similarly, y element of J2 definitely. So y cannot be in F2. So that's what we will do. For each n in I, y is in Jn, and hence y does not belongs to Fn for each n. For each n is not required. Already we have written in the game. Okay. Therefore, y is not inside union of all Fn's, because y does not belongs to each of that F1, F2, so definitely it won't be in the union of all these F1's. But what is this? This is nothing but R, that is what we assumed. So y is a real number. So y is a real number, we have assumed here, but y does not belong to union these things. So but this is equal to R. This is the assumption we made. You see here, I assume that R equals to union of all Fn. So this is the contradiction. That y is a real number, we have assumed, but that y is not in R. This is a contradiction. Because all the sets are real subsets of real numbers only. So this I should definitely be inside R, but here we are telling that y does not belong to R. Just now we said y belongs to R, but in this step we are getting the conclusion that y does not belong to R. This is a contradiction. Therefore, why we are getting a contradiction? Because we assume that real numbers R is a first category. Therefore, R is of second category. Hence the Bayes category theorem. So to be very careful. So you have to think what is J1, I1, J2, I2. There are three different comparisons. It's x1, x2, x3. Okay. Then f1, f2, f3. Then I1, I2, I3. Then J1, J2, J3. So finally we compare only f1 and Jn. So this is how it goes. So first f1. Then we create one element x1. Then from this we create one set I1. then finally we create J1. Similarly, F2, X2, I2, J2. Like this it goes. Finally, we compare these two sets only. All these things and produce a contradiction. Okay. So this completes the Bayes intersection theorem.